Welcome back to Computer Lessons.
Silicon processors possess no inherent concept of human language or visual symbols. Every letter, word, and sentence exists as a series of abstract numerical values within system memory. This mapping converts the physical state of transistors into the text seen on a computer screen. Early computing required a universal method to translate these electrical pulses into readable characters. Without a standard protocol, different machines could not exchange text files without total data corruption. Character encoding provides the dictionary that links binary integers to specific alphabetical and numerical glyphs. The history of digital text begins with teleprinter codes used in the 19th century for telegraph communication. The Baudot code utilized a 5-bit system providing only 32 distinct character combinations. This narrow limit forced operators to use shift codes to toggle between letters and numbers. The American Standard Code for Information Interchange, or ASCII, emerged in the 1960s to provide a broader set. Engineers settled on a 7-bit architecture which provided exact 128 unique character slots. This standard forms the absolute bedrock of all modern digital text communication. ASCII reserves the first 32 slots for control characters that manage hardware behavior rather than printing text. These commands include historic signals like carriage return line feed and the bell sound. While often invisible to modern users, these codes still govern terminal behavior and network protocols. The remaining 96 slots contain the printable characters, including the English alphabet digits and basic punctuation marks. This set was sufficient for American English, but lacked symbols required for other global languages. The rigid 7-bit limit created a significant barrier for the expansion of international computing. As hardware moved to an 8-bit byte structure, manufacturers gained an additional bit for character representation. This extra bit doubled the available character slots to 256. Various companies created proprietary extended ASCII sets to include specialized mathematical symbols and European accented letters. This expansion led to the fragmentation of digital text through regional code pages and localized standards. A file created on a Windows machine in Europe might appear as gibberish on a system in Asia. These conflicting standards caused massive data errors during the early growth of the Internet. The term mojibake describes the garbled text that results from decoding a string using the wrong character set. A computer might interpret a binary sequence as a Cyrillic letter, while another sees a Greek symbol. This lack of consistency made global information exchange a constant technical struggle. The industry required a single master list to accommodate every written language across human history and culture. The Unicode Consortium was established to create a universal standard for character identification. Their goal was to assign a unique and permanent number to every symbol used in writing. Unicode identifies characters through abstract numerical values, known as code points represented by the U plus notation. For example, the capital letter A is always mapped to the code point 65. This abstraction separates the identity of the character from its physical storage format. The Unicode space is divided into 16 planes, each containing over 65,000 individual code point slots. Most modern characters reside in the basic multilingual plane, which covers current world scripts. Higher planes store ancient hieroglyphs, specialized mathematical notation, and the ever-expanding list of emojis. Character sets define which numbers map to which symbols, while character encodings determine how bits store those numbers. A single Unicode code point can be stored in memory using several different bit patterns. Choosing the correct encoding is critical for balancing system performance and storage efficiency. The UTF-32 encoding uses a fixed width of 4 bytes for every single character in the set. This approach provides extreme simplicity for programming, but wastes massive amounts of memory and disk space. Most text files would quadruple in size if every character required 32 bits. UTF-16 uses a minimum of 2 bytes per character and became the standard for Windows and Java environments. It handles the most common characters with high efficiency, but requires special logic for symbols in higher planes. This dual nature introduces complexity when processing strings that contain rare or ancient symbols. To handle characters beyond the initial 65,000 limit UTF-16, utilizes a mechanism called surrogate pairs. Two distinct 16-bit units combine to represent a single character in the higher planes of Unicode. This ensures the system remains backward compatible while supporting the entire vast Unicode range. The UTF-8 encoding emerged as the dominant solution due to its variable length genius and extreme storage efficiency. It uses between 1 and 4 bytes for each character, depending on the requirements of the symbol. This dynamic adjustment minimizes space for standard text while maintaining support for global symbols. UTF-8 is backward compatible with ASCII because the first 128 characters use 1 byte. This means an old ASCII file is also a valid UTF-8 file without any modification. This smooth transition allowed for the fast adoption of Unicode across the global web. The algorithm uses prefix bits in the first byte to signal the total length of the sequence. If a byte starts with 0, it represents a single byte ASCII character for maximum speed. Multi-byte sequences start with a specific bit pattern that tells the decoder how many bytes follow. Today, UTF-8 is the default encoding for almost all websites, operating systems, and programming languages worldwide. It provides a perfect balance of compatibility, efficiency, and universal support for every human language. The standardization of this protocol solved the fragmentation issues that once plagued the digital world. The byte order mark, or BOM, is a special character used to signal the bit order in a file. It helps the software determine if the data is stored in Big Endian or Little Endian format. While less common in UTF-8, it remains important for UTF-16 and UTF-32 files. Unicode normalization handles the complex problem of characters that can be represented in multiple ways in code. An accented letter might exist as a single code point or as a base letter plus a mark. Normalization ensures that these different binary sequences are treated as identical during search operations. The supplementary multilingual plane contains thousands of specialized characters, including ancient scripts like cuneiform. It also houses symbols for musical notation and advanced mathematical operations used in research. This plane ensures that the digital record of human knowledge remains complete and accessible forever. Emojis are not small images, but specific Unicode code points rendered by the host operating system. When you send a heart icon, you are transmitting a unique integer in the higher planes. The appearance of the emoji depends on the font files installed on the receiving hardware device. Character encoding also introduces security vulnerabilities through homograph attacks, where different characters look identical to the eye. A hacker might use a Cyrillic letter to create a fake web domain that mimics a trusted site. Modern browsers use Unicode and other safety filters to protect users from these deceptive links. Software developers must handle string buffers with care to avoid errors when processing variable length UTF-8 sequences. Calculating the number of characters in a string is different from measuring the total byte count. Mastering these distinctions is essential for building robust and internationalized software for the global market. In our next technical lesson, we will transition from digital data to the physical machines that process it. We will explore the epic conflict of ARM versus x86 and the future of chip architecture. We will explain why your smartphone and your desktop use different processor logic to think.
The evolution of character encoding has transformed the internet into a true universal library for all human thought. We have moved from simple electrical pulses to a system that captures every nuance of our diverse languages. Do you believe that a single universal encoding system has made the world more connected or more complex? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.